Okay, you see that, right? Can you see the slides?
Yes, sir.
Fantastic. So thanks, and so we start with the sequence of functions, and here is the setting which we will follow mostly. So you'll be given a sequence of functions, but note that it will be from a set X to the extended real line minus infinity to plus infinity. And often, I mean, always, usually it's a non-empty set. So in having this minus infinity and plus infinity, you know that if you take a subset here, the supremum will always exist, infimum will always exist, because you have no obligation, right, to not to find infinity or minus infinity. So you can talk about supremum of Fn and lim sup of Fn from X to that extended line again. Now you define this pointwise. How you do that? So you define sup of Fn at the point X for every X, little x in big X as, so you look at this sequence Fnx. So now Fnx lives here, and you can talk about sup, which is going to exist because, you know, if it is.
Hello.
Yes.
મિત્ર મારી એનસ્ટ્રી માં પડી છે મારા દફતરમાં માનવીનું ઓલું ડેસ્ક છે ને ત્યાં મારું બેગ પેલું દેખાણું પેલા એમાં પેલા ખાનામાં છે એમાં એક મોબાઈલનું ચાર્જર રહી છે બે વસ્તુ દઈ જાવ ને એવું હોય તો આખું બેગ જ દઈ જાવ ને
Please stay muted, Prashant.
Oh, I see. I thought this mathematics were different language. That's fine. Okay, so you are going to get an element. The right hand side is going to be an element over here, right, for every fixed X. So that's the definition of sup of Fn. So one more time, it's defined pointwise. Similarly, you define lim sup of Fn pointwise. So for each X, you look at the lim sup of this sequence, and that's the definition of this. Okay, that's our definition. Fine. So once you have this lim sup Fn, you can also talk about lim if inf Fn, and remember this duality in the sense. I think I made a mistake. So lim inf of An equals to minus of lim sup of minus An, right? So this is going to be minus An. Okay, you agree? So if you take this trick, you can similarly define or quickly define lim inf of Fn as well, pointwise. Okay. Any question in the definition? We'll talk about some examples, you know, today, maybe some homework, maybe in the next lecture. Okay, so here is the theorem that if your sequence, so now you start with a measure. See here, there is nothing to do with measure, etc. Okay, so now you have a measurable space X, and you have a sequence of functions from X to this minus infinity plus infinity. Then your sup of Fn and lim sup of Fn, and subsequently lim inf of Fn also going to be measurable, and that's a very important property. So one more time. If you have a sequence of functions, then sup, lim sup or lim inf, all of them going to be measurable. And as usual, you have to be always careful. If I think not in this case, with having this minus and plus infinity. Okay, so you have to be sometime careful. Perhaps not in this case. Here, having this is kind of blessing because you can always talk about all this. Talk about the definition of sup and inf, etc. So how to prove this? So I'll prove the sup Fn part first. So we call G as this. Now I go this part a little slow so that you understand how to prove something measurable or not. So remember, you have to prove G is measurable. So how you prove that? You prove G inverse of R open closed infinity is measurable, right? Because this gives you the basic element of the sigma algebra of the topology or the Borel set, Borel sigma algebra on this set, right? So you have to prove this is measurable. You can take this to be closed as well, no problem. Okay, Or you can take minus infinity to R, minus infinity closed, R open, closed, doesn't matter. That is also fine. So if you do that, okay, one of these. So I have considered this. So fix an R, and then you observe that an element lives here. So X lives here. If and only if, by definition, Gx is larger than R, correct? Now, what is the definition of G? G is the sup of Fn. So if sup of Fn is larger than R, I mean sup of Fnx, correct? Sup of Fnx is larger than R, then all of Fnx will be larger than R for all, right? That tells you, turning around, that X is X in the Fn inverse of R infinity for all n, and that tells you X is the union of Fn inverse R infinity. So this becomes set equality, okay? And this is what you have to do often. So this is the reason I showed this computation carefully. Perfect. So this is a trivial equality. Now you want to prove this is measurable. Now you look at this. So this is something like, you know, countable union of some sets, right? What are the sets? Fn inverse of R infinity. But you know, Fn is given to be measurable. So this set is measurable. That's what I've said here. And the countable union of measurable set is going to be measurable, and hence this set, left-hand side set, is measurable, and that tells you G is measurable, right?
So
Yes.
will it be Fnx greater than R for all n or for some n?
One more time. Fnx. Oh, you are asking whether this is true or not?
Yeah, you said
Yeah,
it is true
yeah,
for
it
all
is.
n.
It seems so, right? I mean, look at the definition. What you are saying, this tells you that sup of Fnx, correct, is larger than R.
So there will be some n for which Fnx will be greater than R, right?
You mean it is possible that for some n, Fmx equals to R?
Maybe less than R also.
Is it the case? Less than also? Suppose there is a m such that, okay, let's call this as am. Let's call this
If
Fnx as an, okay? So if an is larger than R, sorry, if sup of an is larger than R, then is it possible that there will be some am such that am equals to R? That is the question you are asking, right? Is it true? Yes or no?
yes, right. If you consider sequence 1, 1 by 2, 1 by 3, the supremum is 1.
What you are saying? 1 by
1, 1 by 2, 1 by n sequence basically.
1 by n, yes. Sup of this is
The
what?
1.
1. Correct. And none of these guys are 1, right? No, but
Only
okay,
one.
you mean even take m is larger than equals to 2, is it?
Yeah, that's okay.
Oh, okay, then you are right. Then I don't mind. I take this to be R and this to be R, no problem. I guess you're right, but doesn't matter.
No,
What?
actually it will be if and only if Fnx is greater than R for some n.
I see. Because I'm taking the sup, right? So
Yeah,
you
if
want
you
to
tell
say
me
for all n but finitely many, is it?
no, for some n means if even if there is one n, we are done. So I should say there exists n Fnx is greater than R.
There exists n. Okay, I have to inspect this from the beginning then. Let me erase this. So I'm having sup of, but I'm in the larger R situation, right? Oh man.
If instead of supremum you start with infimum, then it holds.
Right. Now
And
how to do this? That's what I'm thinking. So this is larger than R. So Well, it's okay, I guess, to say that this is also larger than equals to R for all n. There is nothing wrong, right? But you are going other way. That's the problem. Do I need?
No, we can't say greater than equal to R also, because consider sequence 1 by n. There are terms. I'm starting with 1, 1 by 2, 1 by 3. Only 1 by 2 is strictly less than 1.
This is the problem with online thing.
Sir, anyway, you are taking the union in the last, right? So for 1n, if it works, it will be in the union.
Sir, I'm just saying you should write for some n. Then it holds that it is in the union. When
Okay,
we are
I
writing
follow
in for
because I'm not very comfortable with this system. You know, my eyes are burning as well. So what you said for some n, that's what you mean?
Yeah. Yeah, in this line also for some n, in another line also for some n, and ultimately it is in the sequence.
Yeah.
Ultimately
Yeah, because
it's
I'm
in the
taking union, right? I'm taking
Yeah.
union. Okay.
Right.
Yeah. No, I think you are right. Thanks. In any case, so thank you for that. And now, is it going to be strictly larger than R? Yes, that part has to be strictly, right? And then this is also open. This is also open. Okay. Yeah, since it is union, it's going to work out. Now I lost time. Anyway, so now is the argument is okay. So this tells you G is measurable and you are done. Now from here, we can also infer if the supremum of Fn is measurable, then the infimum of Fn is also measurable. It's the same arguments because infimum of Fan, if you take a sequence, is going to be minus of sup of minus An. And hence you can consider infimum of Fn as minus of sup of minus Fn, and that tells you infimum is also measurable. So this is the statement. So infimum is also measurable. Now, once you know sup inf both make sense, then you go to the second part, that lim sup of Fn. So you look at the definition as this is Hx is lim sup of Fnx, and by definition this is nothing but inf of sup of Fix, where I ranges from k to infinity for every fixed k, and this is going to be inf is going to be over k. So call these guys gkx, and you are taking the supremum of some sequence, right? So this gkx is the supremum of a sequence, and by part one, this is measurable, and this dotted part, then the infimum is also measurable, and hence the lim sup, which is this, is measurable. That proves the second part, right? So is it fine now? The second part. And for the record also, I said that lim inf of Fn is also measurable, which I already pointed out, that the duality is right here. Okay. All right. So now I move on to the important concept, what I think Rudin also called building blocks. So suppose X is a measurable space and E is a subset of X. So you just take a subset of X and define the characteristic function, also known as indicator function. Kindly allow me to record your lecture. It's already recorded. I mean, Ashkar is asking to record the lecture. So why have to record? It's been recorded, right? So, well, absolutely up to you. All right, so indicator function is defined by chi e. So this is the notation at the point x is 1 if x is in E, and 0 if x is not in E. Okay. So note that chi e inverse. So again, if you go back to the definition of inverse function, R to infinity, R open, I guess, yeah, R open and infinity closed. Oh, I'm sorry, I'm not taking infinity here. So this is also open. Okay. So R infinity is empty set if your R is larger than equals to 1, and it is E if r is smaller than 1. Am I saying right? Yeah, correct. I don't think there is any problem if you write r, if you replace r by extended 1 as well. Not a problem. After all, we are going to talk about measurable functions, so this is also fine. So from this thing, this fact, you observe the following, that chi e is measurable if and only if e is a measurable set. Okay. And as I said, this characteristic or indicator functions plays the role of building blocks of measurable function. That means when you talk about measurable function, general measurable function, roughly you want to realize or represent that in terms of limit or one way or other of indicator function. Okay, we'll see that slowly. That is the reason we say this as to form building blocks. Okay. So from now on, well, X will be measurable space. Mostly whenever you see X, it should be clear from the context whether it's a general set or measurable set. By the way, in this part of definition, I don't see anything to do with measurable. Okay, so you indicator function can be defined without measurable space also. So I don't see any point. So let X be a set is fine. Now here you can say that suppose X is measurable. All right, so here is the definition, another important definition, that's a simple function. So I had little s, but then I realized that s referred to sigma algebra in our lecture, so I changed it to phi. So phi is a function from X to C. Note that I have written C here. Okay. I guess this infinity is not counted. So let's leave this part. All right. So here the infinity part is not included. I think there is a point also. That's what I've said here. So you define, so you take a function phi from X to C. Note that I have taken C. So C includes also real line, but not plus minus infinity. Okay, C doesn't have plus minus infinity part, it's only the real part. So it's a function. If the range of phi is a finite set, then we say that phi is a simple function. Okay, so you take a function whose range has only finitely many points, then you call it simple function. Simple definition. Okay, the range is very limited. So if you have a simple function and if you assume the range of phi is alpha 1 alpha 2 alpha n, then you can use this characteristic function and you can rewrite phi as sum of alpha I chi ei. Right? What is ei? Ei is those points in X such that phi x equals to alpha I for all I. Or also you can say that this is phi inverse of alpha I. So in other words, if you know a function takes only finitely many value, you just look at the pre-image and consider that set. So this is just the pre-image, right, of alpha I, and you rewrite phi as the linear combination of this simple function. That means the characteristic function. From this definition, a simple homework is the following, that S set, S is, I'm sorry, not S, phi. The function phi is measurable. This function phi is measurable if and only if all these EIs are measurable. So this S is Rudin's notation. Okay, so I have to move. Okay, any question? Then I move to a very important result, and the theorem states the following. Suppose you have X, a measurable space again, and F is a measurable function. Note that I have taken 0 to infinity. That means suppose, okay. Then the theorem says that then there exist simple measurable functions phi n on X such that 0, so phi i's are all, phi i's forms an increasing sequence and dominated by F pointwise, number 1. Number 2, the pointwise limit of phi n x equals to fx. That's true for every x. So when you say part A, part B essentially says that phi n x is increasing and it converges to f. So this is our notation, okay, because of this. So the statement is clear. So you start with a measurable function, and then you get a sequence of simple functions, increasing sequence, non-negative as well, such that the point-wise limit is equals to f. Okay, this is a very, very handy tool, and you are going to use it on and often. So this already tells you that simple functions play a very important role, because you can approximate simple a general measurable function by simple function. However, you shouldn't be too happy to see this yet. It's a great one, partly because the convergency is pointwise. We don't have any other thing to also talk about, but there is something called uniform convergency, and we'll talk about that. So from that point of view also, this result is good. Okay, so let's try to prove this. I differ from Rudin a little bit. Of course, this is a standard proof, but Rudin left it very neat and 4 or 5 lines proof, and I don't think it is justified, at least if I explain this to you. Okay, so I try my best, little bit of maybe homework somewhere here and there, I don't know, maybe I have done it full. So here you go. So you start with a non-negative measurable function f. Okay, it could take infinity, and that's a bit of concern, and that's where you have to work a little bit more. Here you have to be a little bit careful. And I go as follows. Suppose you fix n. So for each n, I'm going to construct phi n. So my goal is clear. I'm going to come up with phi n with all these properties. Okay. Now given n, I fix little x from big X. Now I'm going to define my phi n. Okay. So once you have little x, then you have two options. Fx is larger than or equals to n, or fx is smaller than n. Okay. So first option, let's settle this. If fx is larger than or equals to n, then you define your phi n x as n. Number one. Now assume your fx is smaller than n. If fx is smaller than n, here is the trick. So then you look at the value of fx, and you do the following: you round down fx to the nearest integer multiple of 1 over 2 by n. In other words, so you look at the interval 0 to n. That's the interval you are looking at right now, because after n, your phi n is defined, which is kind of n, right? Which is n. So you look at 0 to n interval, and you subdivide this interval of you divide this interval with smaller subintervals of this form: m minus 1 over 2 power n to m over 2 power n, and you allow your m to range from 1 up to n times 2 power n. Okay, you look at that, and you look at your value fx, where it falls. So if your fx falls in this interval, you take the least guy. So that's what I said. We round down fx to the nearest integer multiple of 1 over 2n. So you look at this guy, and that's the value of your phi nx. And so this is fx less than n. And your fx is larger than or equals to n, you just have n. So is the definition is somewhat clear to you? Can I ask you to draw the graph as a homework? So draw the graph. Oops, I'm sorry. Draw the graph for phi1, phi2, and phi3. Draw. Of course, you have to take a function f. So you take a simple guy, maybe a parabola, maybe something. Do it for parabola. It's fine. You understand the definition? So one more time, what you do, you fix an n, and you then fix an x, and then you look at the value of fx. If fx goes beyond n, your function is n. And if fx is smaller than n, just look at the nearest integer multiple of 1 over 2 power n, and you define that fellow as the value of pnx. Okay. So this n is a bit of tricky part. Okay, so as I have left a note, this takes care of the unbounded part of the function. See, this phi can be, f can be unbounded, right? It can take infinity. So some value of f could be maybe unbounded. Okay, so so that is the reason you want to take care of you take care of that part over here. So if f is bounded, then after certain stage, suppose f is bounded, suppose f doesn't take infinity at all, so then what will happen? After certain stage, this n part will disappear, because you are not going to for a fixed x, you are not going to find you are going to find some n naught such that fx is less than n naught, right? So this will terminate at certain stage, and I'll explain this part in the proof. Okay, so is there any question in the definition? No. Okay, now look at this definition. If you look at this, this is m minus 1 over 2 power n if fx is in this region, right? So if that is the case, so the value of fx is going to be larger than or equals to m minus 1 over 12, the real value of fx, right? Fx has a precise value, the real value is going to be lesser than larger than or equals to m minus 1 over 2 power n, however smaller than m over 2 power n. So if fx is smaller than n, then the difference of fx and phi nx, by the way, difference I'm saying, fx is going to be larger than or equals to phi nx, because fx lives somewhere here in this region, right? So this will be differed by at most 1 over 2 power n, right? In other words, fx less than 1 would imply this difference is positive, less than or equals to 1 over 2 power n. Do you buy this? Right. Therefore, now I construct the interest, the set of interest. So I set a. This is these are all index. So a power m sub n. M is going to run over here, because you have this many subintervals. So a power mn as those x from cap x such that fx falls in this region. Okay, that means this is nothing but f inverse of this subinterval, and your bn is just the leftover. So bn is those x such that fx is larger than equals to n. That means f inverse of n to infinity. Okay. Now these are measurable. Why? Because f is measurable. So these are measurable sets. So right. So I mean Borel set or open set. So these are measurable subset of x. Correct. And in this case, if you accept this representation of this set, then look at this definition. The definition of phi n is just this, right? Maybe I small, a little small font so that you can see. Do you see that? Right? So that's the definition of phi n, and that's carefully manufactured. Okay. All right. So once you have these, oops, sorry about that. All right. Once you have this, then again, by construction, the way you construct, your phi n is going to be increasing. Number one. And then you look at pointwise thing. So now you take x and think fx as a finite number. I'm going to prove if fx is finite, then phi nx will converge to fx. And even fx is infinite, still it will converge to, still phi nx will converge to fx, monotony. Okay. So, all right. So suppose fx is finite. If it is finite for some x, then that would tell you what? There exists an n naught natural number such that fx will be dominated by n naught, right? And if it is dominated by n naught, then what will happen? Your fx minus phi nx is going to be 1 over 2 power n for all n larger than equals to n naught, right? And that tells you your phi nx is going to converge to phi x, and that's part A. That's number one. And now if you assume your fx is infinity, that means your fx is larger than equals to n for all n. Yeah, okay. So if it is infinity, it is larger than all n, right? So that would tell you what? If fx is larger than equals to n, that means your value of phi nx is going to be n, right? So by definition, phi nx is n for all n, and that also tells you phi nx converges to fx, which is infinity. correct? So this is your part. So phi nx converges to fx, which is infinity. And this part A and part B together tells you your phi nx converges to fx. That proves the result. So any question? Oh yeah, that's yeah. So no question. All right. So one more time, look at the construction of phi nx. It's this. This is, I think, the same construction of Rudin, but Rudin did it very quickly, which is fine. He want you to think, okay? Not like us. He want you to think. And that's the best way to do mathematics. And, yeah. All right. So here is a remark. The remark is the following. Suppose you look at the set A, which is what is this? Oh, I see. So what you do, you collect. Suppose m is a positive number, okay, and consider f is given. Oh, I see. There are too many. I think I'm continuing this from the previous observation. So suppose in the setting, in the above setting, that means f is a function measurable, and it takes positive and this possible infinite value. And you do what? You take a positive number m, okay, and then you consider fx less than m. I'm sorry, something is not right. Why I am making it? I think I can make it simple.
Sir, it will be, I think, set of all x in A such that fx is less than m.
Set of all
X in A.
set of all x in A. Oh, you mean I should bring it over here?
Yes, sir. This set which you have defined such that.
Is that what you mean?
Yes, sir.
Yeah. That's how one should write a set, right? All right, so let's see that. Suppose A is a subset of X such that your fx is smaller than m. What does it mean? So m is given, right? Okay. Well, I want to prove that if you have a, okay, let's look at the last line. Okay, I think I made something confusing here. So you want to prove that phi n converges to f uniformly on a set A, where A is a subset of X, where the value of where the function is bounded by M. Okay, so A is a set where the function is bounded by M. So is that how I write it? So X. Okay, there you go. Okay. So this is a late night effect, you know. So this is capital X. I think this is the one. Okay. So A is a subset of X. It collects those points such that f is bounded uniformly on by M. So F is uniformly bounded by M. That's what I'm saying. And if that is the case, if that is the how you construct A, if you get such an A, on that particular A, you can actually say a little more, because in that case, your fx minus pnx will be 1 over 2 power n for all n larger than equals to m, right? And in that case, your right hand side will be x free, and that's the meaning, that's the way you say phi n. See, in this case also phi n converges to f pointwise. However, this pointwise will be uniform because this is x free, and then you can conclude your phi n converge to f uniformly. Okay, so if you consider a subset of x where f is uniformly bounded, that's the statement. So if you consider a subset of x where f is uniformly bounded, okay, then on that particular set, your phi n is going to converge to f uniform. And uniform convergence is stronger than pointwise convergence. And as you know, this helps you to talk about passing the limit of derivative, integration, etc. So this is a bit ideal situation, and that's exactly what you can expect. You cannot expect anything better than this, because there is nothing to talk, nothing to worry about norm or metric, etc. in this setting yet. So this is the best thing you get. So one more time, let me state this before I go to the next slide. So if you have a measurable function, you are going to find a sequence, increasing sequence of non-negative and increasing sequence of simple functions, simple measurable functions. Important, very important. It's measurable, such that phi nx converge to fx for every x. That's a statement, and this convergence is uniform if you're on those sets where f is uniformly bounded. Okay. All right. Now here is a very simple fact which you should do. Suppose phi1 and phi2 be simple functions on a measurable space X. Then a phi1 plus phi2 and product, so it's a linear sum, and phi1, phi2 the product, they are also simple functions. That means the set of all simple functions forms an algebra. Now let me see what I'm saying, what I'm trying to do with measurable space. Does it work without measurable space or what? Okay, it works without measurable, but if you say simple functions, I don't think there is any measurability required in this picture. So suppose phi1, phi2 be simple functions on X. Then these are also simple. That means the set of all simple functions forms an algebra. Is it acceptable to you? I guess so. Right. Okay. So if you say this, okay, the point is that if you assume that phi1 and phi2 are measurable simple function, then these are also measurable simple functions. So that's why measure comes, right? So if you assume that phi1 and phi2 are not only simple, but they're also measurable, that means measurable simple functions, then the linear combination and the product are also measurable simple functions. So that's how you can explain the measurability part. Otherwise, I don't see any measurability issue. Okay, so far, this is what we have done. What we have done, we have started with a non-empty set X, and then we developed the idea of measurable space. So what is measurable space? It is the ordered pair, X comma S. What is S? S is a sigma algebra on X, right? And right now we are going to do something more. So we are going to talk about, after measurable space, you're going to talk about measure space. So see the difference between wording, this wording, so it's slightly different, measurable to measure. So we are going to talk about measure space. What is measure space? It is a measurable space along with a function mu, and that mu is known as measure. Okay, so this is my definition. So suppose X S be a measurable space, a measure mu is a function from S, the sigma algebra, to 0 infinity. So it's non-negative function, but it can take infinity. Such that there are two properties. Number one, the measure of empty set is 0 always, and the measure of disjoint union of AN. So you take a sequence of AN from S, sigma algebra S, and assume that AI intersection AJ is empty for all I not equals to J. That means the disjoint union. And I think we have a better way to denote this, right? This is how I write, and most people like to write. Disjoint union means you write this way. Okay. So it's a disjoint union of A. The measure of that is going to be the sum of the measure of A. That's the definition. So a measure is a function from the sigma algebra, from the given sigma algebra to 0 infinity, such that the empty set measure is 0, number one, and it's what we call countably additive. In other words, if you take a sequence of disjoint measurable sets, then the union of the measure of the union is sum of the measure, right? So the measure of the union is the sum of the measure. That's the condition. A definition: a complex measure mu is a function from S to C, and when you should realize that when you talk about complex, there is no infinity or etc. Okay, so it's a function from S to C, such that again the same thing. The measure is measure of the empty set is 0, and it's countably additive. Okay. Now, if mu is a measure on X, then we say that X is mu, this triple, a measure space. So what is measure space? A measure space is a measurable space, first of all, and along with a measure, mu defined on the sigma algebra. Sometimes we just say that mu is a measure on X. So when someone says that mu is a measure on X, then what you should understand? You should understand two things. So first, there is a set X. Of course, X is there, which will be stated, but you must understand there is a sigma algebra there, and mu is a measure function defined on the sigma algebra. Okay, so is the definition is clear? Okay. All right. So if the definition is clear, I give you simple examples. First one is A, what we called the counting measure. So you look at a set X and look at the sigma algebra as P of X. So this is your sigma algebra X. Okay. This is your sigma algebra X. And you define mu from P of X to 0 infinity. So you take any subset E. That means it's an element of the power set. Mu E is the cardinality of E if E is a finite set. So that you are going to get a number if it is a finite set. That's the cardinality, number one. And in case it is infinite, then there is no finite number. Then you just assign infinity. You see how this infinity is helping you. Otherwise, it's an ambiguity. Countable set, you may want to say infinity, as if not, whatever. I mean, this is very difficult. Okay. So you just simply say that finite set, the number of element, infinite set, infinity. And can you please check this is going to be a measure? So it's going to you're going to prove the part which might be intriguing a little bit is that this part, right? This part 2, correct? So please do that, even for finite set and infinite set. In any case, when you define in this way, this measure is known as counting measure. It's a very important measure. You will see, I think, in next few lectures also. So when you do this thing, you also consider your X to be the set of natural number, as well as you can consider X to be just the set of finite set 1 up to capital M. So for these two particular case, consider the counting measure. Try to understand what is the real meaning of it. Okay. Second one is another important example. That's called Dirac measure or point mass measure. So it goes as follows: fix an X naught from X and define mu from power set. So here also the sigma algebra is P of X. You define mu of E as 1 if X is in E, and you define it as 0 if X naught is in E, and if it is If it is not there, then you call it is 0. So again, you prove that it is going to be a measure, and I think it's very easy, right? It's very easy. So when you take disjoint union of countable set, then it's not going to be difficult. There is a popular notation for this mu, the direct data measure, that's del of x naught. And third example is also good, slightly different than the previous two. Suppose you have an uncountable set x, and consider the sigma algebra, it's different, not p of x. Take all, so we talked about this, and I think there was a mistake when I said this the first time. I don't remember. So take those subsets of x such that either e or e complement is countable. So either E is countable or E is co-countable. That's another way to say. E is co-countable means E complement is countable. So one of them must be countable, and the full set space is uncountable. Otherwise, this doesn't make sense. It will be full of px otherwise, right? Yeah. So in this setting, you define your mu from s to 0 infinity s is over here as follows. Mu e is 0 if e is countable, and mu e is 1 if e complement is countable. Okay, and I ask you to prove this is a measure. So this is a typical example, one of the typical examples of probability measures, so called, because the full measure of the, what is the measure of x here? Can you see what is the measure of x?
1.
1. Yes, why not? Because 1 complement is what? Empty.
It is empty, countable.
Oh, I'm sorry. Yeah.
So it is 1.
Yeah, because of this, right? Yeah. Fine. So these are 3 examples, and now let's see some properties. And here is one. Couple of mostly taken from routine, but I explain. So now I assume x s mu is a measured space. So one more time, x is a set, non-empty set. S is a sigma algebra, and mu is a measured function defined all over S. And mu can take infinity also. That's you should keep this in mind. And we have to talk about infinity, because I told you in the lecture 1 that Lebesgue measure also take care of unbounded function. So you have to play with infinity. First property, that it's kind of monotone. That means if A is subset of B, then mu A is subset of B. Sorry, mu A is less than equals to mu B. For all, don't forget, AB should come from S. Don't say AB for any AB. No, it's mu defined on S. Okay. Second is what we call sub errativity. That means if you take any sequence of measurable sets, so this is measurable sets, right? Sequence of measurable sets. In that case, mu of union of an is lesser or equals to sum of mu of an. Remember, this is actually equality if your ans are disjoint, mutually disjoint, right? But in general, it is less than equals to sum of mu a. Third property. Okay. Third property is that an, if you take a sequence of measurable sets, that means a sequence from S, and if it is increasing, then the union of an, that measure is the limit of mu of an. It's kind of continuity type, right? I mean, you can think this as the limit of an, right? Union you can consider as the limit of an, that limit goes out. In essence, it's kind of continuity. However, it is increasing. While you do for decreasing, it is very close. If you take the same type but decreasing, then taking union doesn't make sense, because immediately you want, right? So taking intersection makes sense. So you take the intersection. There also the limit is mu of the measure is limit of mu of a. However, you need to assume the measure of the large guy, the big guy, the fat guy is finite. If it is not finite, it is not true. Okay, so these are the 4 statements. It's very useful, and on and often you're going to use it. So keep this in mind, and I give you a proof. So first is what? You have to prove that it's monotone. So A is subset of B, then it's simple. Just you rewrite B as disjoint union of A and B minus A, and that's it. So you write mu B equals to mu A plus mu B minus A, and that tells you mu B is larger than equals to mu A. Is that right? Are you confused why I'm saying is that right? This is trivial, right? This is trivial, right? Oh yeah. You know why I was confused a little bit? Because my infinity is there. So do you understand? So when you say infinity, then you have to think about those already, but here it's all right. Okay. There's a possibility that mu A, mu B minus A could be infinity, right? So you have to be careful. Second property is the sub errativity. So I want to prove this inequality. An is arbitrary but measurable. So I proceed as follows. I define B1 as A1. Then I define B2 as A2 minus A1. And subsequently I define Bn as An minus union of Aj from j equals to 1 to n minus 1. So what you are doing, you are taking A1 first, and then you take A2, but don't consider A1 anymore because it's considered. And this is how you go. This process gives you all this Bn in S, you agree? Because S is closed under what? S is closed under all those operations, countable union, countable intersection, difference, right? So your Bn's are going to be S for all n. And by construction, Bi intersection Bj is empty. Therefore, the disjoint union of Bn is going to be equals to union of A, right? Once you are in this situation, you can invoke the definition, the property of mu, and that tells you the measure of union of An is going to be, I'm sorry, this is, of course, this comes from this equality, but this equals to the sum of these comes from the definition of measure, right? And finally, measure of Bn is what? Measure of Bn is dominated by measure of An by part 1, rather, oh yeah. So Bn is, do you see that? Bn is
subset of An.
that's right. So this is dominated by measure of An, and hence you get this inequality. So this less than equals to this. Fantastic. And now the third claim. Third claim is what? It says, suppose you have a decreasing, I'm sorry, increasing. What we did here? Oh, this is just sub errativity. So this part 3 is what? Part 3 is, okay, if you have an increasing, then this happens. So let's go here. So it's increasing, then we have to prove this equals to this. Fine. Let's move on. As I said, define Bn as above. So how you did it? Like this. But you see, if this is increasing, your B1, if the ANs are increasing, then B1 is of course A1, B2 is A2 minus A1. Fine, it makes sense. But Bn will be what? An minus union of Aj from 1 to n minus 1. But then, since it is increasing, here you will get only An minus 1. You agree? So Bn is going to be An minus An minus 1. So this is how you define. And once you define this way, then you can, in the like this proof, you can say measure of union of An is the measure of, disjoint union of Bn is going to be equals to measure of Bn. So you go to this level. So I take that. So measure of union of An is going to be measure of Bn sum, right? Now you consider this Bn the way you did here. So since Bn is An minus n minus 1, the proof of 1 means this part. The proof of 1 implies mu Bn equals to mu An minus mu An minus 1. Or also you can rewrite this disjoint union of so on and so forth. So you get this, and you say this is true for all n larger than equals to 1. And if you say n equals to 1, there is a little problem because you don't have A0, and you define A0 to be empty set. then it's fine, no problem. And the measure of empty set is 0, so you're fine, good to go. All right, so in this inequality, you find measure of Bn for each n as this, right? Measure of Bn is this. So if this is the case, then you look at the sum, and the sum, what is the meaning of the sum? The meaning of the sum is the limit of partial sums, right? So you look at the partial sum of this series. So what will be the partial? It's a telescopic series, right? So the nth partial sum will be what? Nth partial sum will be mu of an. Do you see that? Right? So mu bn is this. So the nth partial sum will be this one, and all will be cancelled, correct? So if nth partial sum is mu of an, and since you are in the zero infinity situation, so infinity is included, so the limit, the sum is going to converge where? The sum is going to converge to the limit of the partial sum. The limit of partial sum is now nothing but limit of n goes to infinity mu of a. That proves the result. Okay, any question? Fourth part, and I have rewritten it over here. So now you have a decreasing sequence and the fat guy of measure, finite measure, that's assumption, and then I have to prove the intersection is, measure of the intersection is the limit of measure, right? So from this picture, I go on to construct an increasing sequence, and that's not hard. How you do that? So first you take Cn, I'm sorry. Oh, I just straight away define Cn. So Cn is A1 minus An. A1 minus An. Okay. Cn is A1 minus An. Since it is a decreasing, this makes sense. And then you are going to get an increasing sequence. And by this definition, measure of Cn is measure of A1 minus measure of An for all n. Right. And by definition, union of Cn will be what? Union of Cn will be A1 minus intersection of An. That's simple set theory, follows from here. Now you are in a position to apply part 3 because you are in union. So the part 3 tells you the previous step, tells you the measure of the union is the limit of the measure. Right. So the measure of the union is limit of the measure, and this union is what? This union is this minus this. That means measure of A1 minus measure of the intersection. That's your interest, by the way. And the right hand side is what? Measure of Cn. What is measure of Cn? Measure of Cn is measure of A1 minus measure of A. Measure of A1 minus measure of A. Right? All right. This is independent of n. So since you are in infinity situation, your measure can take infinity, all that, your limit goes inside. You don't care about this guy, but limit, and this limit goes inside, and this is free and free. And then you are in a situation, mu a measure of A1 minus something equals to measure of A1 minus something. And from here, if you know measure of A1 is a finite number, then you can cancel. If you don't know it is finite, then you cannot cancel. Okay. So if measure of A1 is infinity, then we are in what situation? We are in infinity plus A equals to infinity plus B situation. And remember, I said all the ordering, but I have not said infinity minus infinity situation. I have not said that. This doesn't make sense. This you don't allow. Okay, so you have to avoid this kind of situation because we do not know infinity minus infinity. We do not say that. We have not defined. Okay, so in that case, if you assume the measure of A1 is finite, you can then cancel, and then you can say they are the same. That's the reason I said measure of A1 is finite. And if you want an example where this is necessary, then I recommend you to think about counting measure, the one I pointed out, or if you are in hurry, you look at Rudin's example on page 70. This is a simple example. I do not want to repeat it. This I got because I thought this page is free, so I stop with something. So this is where I want to stop. Thank you very much. If you have any question.